if we have two functions added together, two expressions that define functions added together, we looked at last time and saw that if we have the derivative, well, if we have f of x plus g of x, we can find the derivative of f of x, f prime of x, and the derivative of g of x, g prime of x, and all we have to do is add those together, and that gives us the derivative of the sum. Namely, the derivative of the sum equals the sum of the derivatives. We went there, we did that. Didn't prove it, but we looked at some examples and they seemed like they worked out okay. If we have a product, the derivative of f of x times g of x, we can find the derivative of f, we can find the derivative of g, and we could even multiply them together if we wanted to, but if we did, that would not give us the derivative of the product. The derivative of the product does not equal the product of the derivatives. A little bit more going on. We can kind of look at it here, but I will attempt kind of a proof of this. So maybe the proof first, and then we'll look at the definition. ddx of f of x times g of x. If we use the limit definition, this is the limit as delta x approaches 0 of, if we think of this as fg of x, if we were to evaluate fg at x plus delta x, the way we would do that is to say that's f of delta of x plus delta x times g of x plus delta x. So although it's kind of written like this, f of x times g of x, literally that's the product function. So if I want to evaluate the product function at x plus delta x, that's what it's going to look like. So just scoot that up over there like that. So it's the limit of f of x plus delta x times g of x plus delta x minus f of x times g of x over delta x. Delta x approaches 0. Somehow we have to go to what we know. We know something about what's given. What's given is that f and g are both differentiable at x. So somehow we want to write this in terms of the difference quotient, where one would find the derivative of f of x, and the difference quotient where one would find the derivative of g of x. Went ahead in that direction. It won't take long. But there's kind of a slick technique for doing this that somebody a long time ago figured out. Limit as delta x approaches 0. Basically, I want to subtract something and then add that same something in between the two expressions in the numerator. It's going to be f of x plus delta x times g of x plus delta x. Going to subtract it, going to add it, and then I'll have minus f of x g of x. What to subtract, what to add? Well, I want it to be something that's going to involve one of these functions evaluated at x plus delta x, and the other function evaluated just at x. So let's see if this would make sense. We're going to go with f of x plus delta x times g of x. No, we need a g of x plus delta x. Sorry, reverse that. F of x, g of x plus delta x, plus f of x, g of x plus delta x. There we go.
You're adding and subtracting the same thing?
Yes. Subtract it, add it. So I'm not changing the value of the numerator. But what I can do is write this as two separate fractions. This is the limit as delta x approaches 0 of f of x plus delta x times g of x plus delta x minus f of x g of x plus delta x all over delta x. And if you'll believe along with me that these limits wind up existing, we can write this as the limit as delta x approaches 0 of f of x g of x plus delta x minus f of x g of x. That saves a step. Typically I write the sum of the fractions, and then I say the limit of the sum equals the sum of the limits, and then I write the sum of the limits. So this is the sum of the limits. Good things are supposed to happen. The good thing that happens here is that this has a g of x plus delta x and a g of x plus delta x in both expressions there. So I'm going to factor it out. This equals the limit as delta x approaches 0 of f of x plus delta x minus f of x over delta x times g of x plus delta x. Factoring the g of x plus delta x out of each factor in the numerator and then sliding it out next to that fraction. Plus the limit as delta x approaches 0, f of x, do the same thing except with the f of x, factor the f of x out of each of those two expressions in the numerator, and then multiply that by the fraction, g of x plus delta x minus g of x over delta x. Are you worried that we might not almost be done? Are you hoping that we're almost done? I certainly am. What do we know about this expression right here? If f, we're given, if f is differentiable at x. If f is differentiable at x, what do we know about that expression in red? That's equal to, well, it's the definition of the derivative. The derivative f prime of x. Yes, that's what that's equal to. Now, this limit, to save a little bit of space and definitely to save some time, because this gets wearisome really fast. It's been wearisome for a while. The limit of a product equals a product of the limits. So as delta x approaches 0, because g is continuous, how do I know g is continuous? I know g is continuous because g is differentiable. And a function must be continuous in order to be differentiable. So g is continuous. If delta x approaches 0, this expression inside here is approaching x. So the value of that expression is approaching g of x as a consequence of the fact that g is a continuous function. So times g of x when delta x approaches 0. Plus, over here, the limit of the product equals the product of the limits. So f of x is just plain old f of x, but the limit of g of x plus delta x minus g of x over delta x, that's g prime of x.